A-Level Paper 2, Specimen version 0.5. So for this question we've got to try and work out the rate equation. So rate equals K, which is the rate constant, multiplied by the concentration of A raised to a power. The power that A is raised to, the number that it's raised to, is called the order with respect to A. So rate equals K, concentration of A to some power, and then multiplied by B, the concentration of B to a power, and the power of B is the order with respect to B. How do I do that? Well, first of all, I'll look at two experiments where either A or B are the same. So I can see in experiment 1, B has a concentration of 0.26. In experiment 2, B has a concentration of 0.26. So I'm going to choose experiments 1 and 2, and you'll see why in a minute. Because those two are the same, for B, it's going to make life easier. What do? I take the concentration of A in experiment 2 and divide by the concentration of A in experiment 1. And that will be to the power that A is raised to in the rate equation, the order with respect to A. I do the same for B, raised to the power that B is in the rate equation, order with respect to B, and I take the rate 1.89 times 10 to the minus 3 and divide by 2.1 times 10 to the minus 4. Let's see that. 0.36, and I've put to the question mark, that's going to be the order with respect to A, so rate equals A to the question mark, 0.36 divided by 0.12 to the power question mark, where the question mark is the order with respect to A. Multiplied by 0.26, so the concentration of B in experiment 2 divided by the concentration of B in experiment 1, 0.26 divided by 0.26, and that's going to be to the power of B. But it won't really matter because that's going to cancel. Equals 1.89 times 10 to the minus 3, so the rate in experiment 2 divided by the rate in experiment 1. So this cancels. 0.36 to the question mark divided by 0.12. 0.36 divided by 0.12 is 3, so 3 to the question mark equals, do this calculation, equals 9. Now that question mark there, the order with respect to A, 3 squared equals 9. So the question mark here is a 2. 3 to the power 2 is 9, that question mark there is a 2. So rate equals A, concentration of A to the power 2. These numbers here, by the way, the orders with respect to A and B can only ever be noughts, ones or twos. So 3 squared equals 9, that's a 2. Next, I'm going to have to choose the other two experiments to be able to work out the order with respect to B. We've got spoilers. I'm telling you it's a 1, so let's see if we can work out why it's a 1. In these two experiments, I've not got any concentrations the same in either experiment 2 or 3. But it's not so bad this time because I've already got some information from my first calculation. My next two experiments, 0.72, so I'm going concentration of A in experiment 3, divided by the concentration of A in experiment 2, 0.72 divided by 0.36, raised to the power 2, and know that's a 2 because it's a 2 here, multiplied by concentration of B in experiment 3 divided by concentration of B in experiment 2, 0.13 divided by 0.26, and that question mark there is this number, the order with respect to B, equals 3.78 times 10 to the minus 3 divided by 1.89 times 10 to the minus 3. And if you calculate that, this number here is a 2. 2 squared multiplied by, this is a half, 0.5, 0.5 to the question mark. Remember, this question mark is this number here that I'm trying to find out, the order with respect to B, equals, these two numbers divided equal a 2. 2 squared is 4. 4 multiplied by 0.5 to the power question mark equals 2. 2 divided by 4, so if we take this across the equal sign and down to the bottom, 2 divided by 4 is 0.5. So 0.5 to the question mark equals 0.5. It's itself. 0.5 to the question mark equals 0.5. Something that's itself means that's to the power 1. So order with respect to B is a 1. Incidentally, if something turns out to be a 1 here, so if, say for example 0.5 to the question mark equals 1, the question mark is 0. Any number to the power 0 is a 1. So this time it's changed slightly different. You're given all of the data here and you're given a rate equation now. So you're not actually asked to work out the rate equation. You're given the rate equation here and all of the data, and you've got to calculate one of the missing parts in the table. So now it's almost turned on its head. You've been given the rate equation, you've been given this data here, and you've got to work out this missing part here. So let's have a look. Let's do spoilers again. So in experiment 4, where there's data for both concentrations and the rate. So we've got everything in experiment 4. So if we've got everything in experiment 4 here, we've got the rate, 7.2 times 10 to the minus 4. We've not got the rate constant, K. We've got C, the concentration of C, so we can work out C squared, and we've got the concentration of D. We've got everything in that equation apart from the rate constant here. So we put these numbers in, and we can work out the rate constant here. So rate equals the rate constant C squared multiplied by D. The rate in experiment 4, where we've got a complete set of data, is 0.0072 or 7.2 times 10 to the minus 4 equals the rate constant multiplied by 1.9 times 10 to the minus 2 squared, because C squared, here you've got C squared, so you've got the concentration of C, 1.9 times 10 to the minus 2, and it's squared, multiplied by the concentration of D, which is 3.5 times 10 to the minus 2. So you calculate those. I would always work these out first, and therefore you get 0.00072 equals K multiplied by 0.000162. You divide this by this, and K therefore equals 57. So we've worked out K for one of the sets of data. Now if it says a constant temperature, the only thing that will change K, the rate constant, is temperature. So if temperature stays the same, then K stays the same. K is only changed by temperature. Nothing else can change it. So if we've got a constant temperature, we know that K must be staying the same. So if K stayed the same in experiment 5, therefore we can work out, it just wants us to work out K. It actually doesn't want out to be calculated here. I think that would be the next bit of the question. It wants us to use K, which we've done, and it wants the units of K. So what we do then is, rate is moles divided by decimeter cubed divided by seconds. That's always the case. Mole decimeter cubed divided by decimeter cubed seconds is given here, equals K. We don't know the units of K, and we've got a concentration squared, so we've got a mole divided by decimeter cubed, mole divided by decimeter cubed, and another concentration here, mole divided by decimeter cubed here. So what you can do therefore is 3 decimeter cubes on the bottom on this side become 3 decimeter cubed on the top. So if you take them across the equal sign, they come to the top. So I've got mole, and I've got 1, 2, 3 decimeter cubed on the top on the other side, and I've got mole, mole, mole on this side on the top. If they go across the equal sign, they go to the bottom, and they've gone on the bottom. Now I can cancel, so I can cancel a mole and a mole on the top and a mole on the bottom. I can cancel a decimeter cubed on the top and a decimeter cubed on the bottom, which will leave me 2 decimeter cubes on the top, and it will leave me a second still on the bottom, and a mole on the bottom. So now what I do then is I take mole and mole go up to the top, and a second goes up to the top. If they go up to the top, they become -1, so that becomes S to the -1, mole to the -1, and mole to the -1. And then you add the 3 and the 3 becomes a 6. The S to the -1 just stays the same, and a mole -1 on the top becomes a mole -2. So that's your units of K. I think the next question will probably be to work out to be calculated here. calculate a value for the initial rate in experiment 5. Indeed it is. So let's have a look at that. So we've got rate equals K multiplied by C squared multiplied by the concentration of D. We know K has not changed because the temperature has stayed the same. It's a constant temperature and there's only temperature that would change K, so that's staying the same. It's going to stay the same. And then we put the numbers in. From here, 3.6 times 10 to the minus 2 is the concentration of C squared, so that needs squaring, multiplied by 5.4 times 10 to the minus 2 concentration of D. There, and we run it all out, and the rate equals 0.00399, and we've been given the unit, so that's fine. So the rate equation for a reaction is rate equals rate constant multiplied by the concentration of E. Explained qualitatively, so that's just using words. Quantitatively is numbers, qualitatively is just words. By doubling the temperature has a much greater effect on the rate of reaction than doubling the concentration of E. Well, first of all, you've got to comment about temperature. Temperature is important because a reaction only goes ahead when the molecules have equal to or greater than the activation energy. So that's the first thing you've got to say. And then you've got to say that doubling the temperature causes many more molecules to have this activation energy. Whereas doubling the concentration of E only doubles the number of collisions. You don't know whether they're going to be successful or not. They'll only be successful if they've got the activation energy. So just doubling the number of collisions doesn't mean that they're going to be successful ones. So there's three parts for that. First of all, saying that reaction occurs only when molecules have an energy equal to or larger than the activation energy, or activation energy is the minimum amount of energy required for a reaction to occur. Doubling the temperature causes many more molecules to have that activation energy, whereas doubling the concentration of E only doubles the number of collisions and the number of collisions, therefore the collisions may not therefore be successful. Now we've got equation here, natural log of K ln K equals natural log of A take away activation energy divided by RT. That's all it's given to you. It's the Arrhenius equation, and you've just got to put some numbers in. So all we've got to do is we write it out and then we say ln K equals ln A take away activation energy divided by RT. So what I'm going to do is I'm going to take away EA activation energy divided by RT to the other side, and that becomes positive, and I'm going to take ln K across to the other side, and that becomes negative. So we now have positive EA divided by RT on the left hand side equals ln A take away ln K on this side, and we just put some numbers in then. The only thing we've got to be careful of is that it says the gas constant is in joules per Kelvin per mole, and it wants it in kilojoules. So I've got to convert that joules into kilojoules. Now a joules into a kilojoules, small into large, is a divide by 1,000. So 8.31 divided by 1,000 multiplied by R. So RT is 8.31 divided by 1,000 multiplied by 300. That's the temperature, 300 Kelvin. So I've got RT here, and I've got R in kilojoules per Kelvin per mole. I've got it in the right value here. You could just work it out in joules and then divide by 1,000 at the end if you wanted to. I've just divided by 1,000 here to get my joules into kilojoules at this point. Equals natural log of A, which is the natural log of A is 2.57 times 10 to the power 10. Take away natural log of K, ln natural log of 0.00651. So I've just got these values from the question, and therefore I've got activation energy. I've multiplied these numbers out, worked these numbers out, is 2.493 equals 20. This works out as 23.97. Take away, this one's a negative number, minus 5.03. Two negatives, by the way, will equal a plus. So, and I've this is divided by on this side, so it's going to be going across the equal sign. It's going to be a multiplied by activation energy equals 2.493 multiplied by these two numbers now added together, and it'll come out as 72.3. So isooctane's drawn here as a skeletal formula. So there's a carbon at each of these points here, 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 and at the ends here, here, and here. So I've got three methyl groups here, and I've got a methyl group. I've got a carbon chain of 1, 2, 3, 4, 5. So I've got some kind of pentane. Give the name for isooctane. So I've got 1, 2, 3, 4, 5. I've got 5 as long as chain. So it's pentane, and if I start labelling from the right hand side, these two methyl groups here, and I've got one here, these two methyl groups will be at number 2, and this one will be at 3, 4. So I've got a methyl group at number 4 and two methyl groups at number 2 are labelled from this end to give lowest numbers. So I've got trimethyl pentane, 2, 2, 4 trimethyl pentane. In terms of carbon-13 Nmr spectrum, I'm looking for different carbon environments, that is, carbons joined to different groups of atoms. So which one's the same? Well, I've got a methyl group and a methyl group here bonded to the same carbon, so these two are the same. So I'll label those two blue. Those two are the same. Now this one here is the only carbon with 3 other carbons bonded to it, so that one's got to be a different colour again. This one here is the only carbon with 2 bonded to it, 2 other carbons bonded to it, so I'll colour that a different carbon again. This one here is the only carbon with 4 other carbons bonded to it, so I'll have that as a different colour. And then we've got 3 methyl groups all bonded to the same carbon, so these 3 must be the same. So how many different colours have I got? 1, 2, 3, 4, 5. So my answer is 5. So question 3.3 says isooctane can be formed together with propene and ethene in a reaction in which one molecule of an alkane that contains 20 carbon atoms is cracked. So cracking means that you've got a long chain breaking into shorter chains. So if we've got an alkane with 20 carbons, it's C20. An alkane, so if it's got single bonds, then you double the 20 and add 2, so that becomes 42, so it's C20H42. We've got the formula of isooctane, which is C8H18. We'll know propene is prop is 3, so it's C3. Ene means it's got double bonds, so you just double that, it's CnH2n, so that's C3H6. And then we've got ethene, which is C2H4, so CnH2n again, so the 2 carbons become 4. Then you need to balance it, so if you balance it, then the best way to balance it is put 2 in front of the C3H6 and a 3 in front of the C2H4, and it should balance up the 20 carbons. How do products of the reaction show that a reaction is thermal cracking? Well, thermal cracking tends to produce alkenes. Catalytic cracking tends to produce rings. Alkenes formed. Deduce the number of monochloroisomers formed by isooctane. Draw the number of monochloroisomer that exists a pair of optical isomers. So the number of monochloroisomers of isooctane, I need to go back to isooctane and see what it looks like. So this is isooctane, so monochloroisomers. So I could have on those blue ones, I could have a Cl. So a monochloroisomer means that a Cl has replaced an H. So on that carbon there's 3 H's and I could replace 1. Now I've replaced the other one, the other blue one, it's exactly the same. So there's 1 there. So it could replace an H on that one or that one, makes the same chemical. There's 3 bonds on that red carbon, so there's an H on there, so it could be that one, so that's 1. 2 on that one, there's 2 H's on that one, so it could be 3. Now that carbon's already got 4 bonds, so it's got no H's, it's got carbons either way, so that one doesn't count. These ones have each got 3 hydrogens on each, but they're all the same, so it doesn't matter which hydrogen I replace with a Cl, it's going to produce the same chemical. So I've got 1, 2, 3, 4. 4 different ways that the Cl can replace an H. Deduce the number of monochloroisomers formed from isooctane. I've done that. Draw the structure of the monochloroisomer that exists a pair of optical isomers. So if I draw out the displayed formula of, or close to the displayed formula of isooctane, it looks like this. Now I've decided to replace this H here, one of these 2 H's, because now that C is a chiral carbon. 1, 2, 3, 4 different groups from that carbon, so that's going to have enantiomers, it's going to have optical isomers. No other H been replaced by a Cl will produce a chiral carbon. one of these H's wouldn't do because I've replaced one of these H's on the C, and I've still got two H's on the C. If I replace one of these H's, I've still got two H's on the C. If I replace this H, I've got two methyl groups still on the C. So there's only that H there, or that one there. You could have the one above it, both the same. Either one of these H's replaced with a Cl is going to give a pair of optical isomers. So these are going to have enantiomers, mirror images that rotate plane polarized light in different directions, in opposite directions. Right. The isomer of isooctane reacts with chlorine to form only one monochloro compound. So I've got to look at something. I've got C8H18. That's isooctane, and I've got to draw it out so that whichever hydrogen I replace with a Cl, there's only one way of there's only one chemical formed. So what I'm looking for is something symmetrical, something really symmetrical. So it doesn't matter which H, up, down, left or right I replace, it ends up forming the same compound when I replace an H with a Cl. So I've done spoilers here for us. Look, it's directly symmetrical. I've got 4 in a line, I've got 3 methyl groups on this end, and I've got 3 methyl groups on this end. Directly, so absolutely symmetrical, up and down and left and right. So it doesn't matter which H of these are replaced, and that methyl group is the same as this methyl group, which is the same as this methyl group, and it's symmetrical left and right. So this methyl group is the same as this one, same as this one. So all those H's are all in the same environment. They're all sort of equivalent to each other. So it doesn't matter which H I replace, I'm going to end up with the same monochloroisomer. So if I replace one of, let's say, these H's here, if I replace all of the carbons with lines, so I've got 1, 2, 3, 4, 1, 2, 3, 4. So I've replaced all these carbon backbones with lines, and then I've drawn a Cl off this one here. But you could draw your Cl off any of those carbons in any direction you wanted to make the monochloro compound. You have to draw the skeletal formula, so you've got to draw it in this way. So I've got monochlorooctane. So I've got octane, so C8, and it would be, if it's an ane, then you double the 8 to add 16, add 2 will be 18. Except one of the 18 hydrogens, so it's C8H18, but one of the 18 hydrogens has been replaced by a Cl. The chlorine contains the isotope 35Cl, so it could be a 35Cl or it could be a 37Cl. However, it's in the ratio for every 1.5 of these, there's one of these. So it's in the ratio 1.5 to 1. Or if I multiply it by 2, it's in the ratio 3 to 2. So if it's in the ratio 3 to 2, 3 35s for every 2 37s, for every 5 of these, if I have 5 of these, 3 of these and 2 of these, I'd have that one, and that one. So it doesn't matter where the Cl is, it doesn't matter where it is on the molecule, then the Mr is going to be the same in this one with a 35, this one with a 35, and this one with a 35, and this one with a Cl, and this one with a Cl. So 3 times out of the 5, 3 occasions out of the 5, it's got a 35 Cl in, and 2 occasions out of the 5, it's got a 37 Cl in. You add up the masses of everything, so you've got 8 carbons in everything, so 8 times 5 multiplied by 12 for a carbon, 17 times 5 times 1 for a hydrogen, and then you've got a 35 and a 35 and a 35, 3 35s and 2 37s, gives, when you add it up, a total mass of 744. To work out an average, you divide by 5, that's the number of molecules that they are, and it comes out as 148.8. Isooctane reacts with excess chlorine to form a mixture of chlorinated compounds. One of these compounds contains 25.6% carbon, 2.56 hydrogen by mass. Calculate the molecular formula of this compound. So, what have I got in there? I've got carbon, hydrogen. It also tells me that I've got some chlorine in there as well. The relative atomic mass of chlorine is 35.5. It's got isotopes, that's why it's an odd number, but it's 35.5. So I can work out if I've got 24.6% carbon, 2.56% hydrogen, then 100% take away 24.6, take away 2.56. I've got 72.84% chlorine in there. I divide by the relative atomic mass of each of them. So 24.6 divided by 12, 2.56 divided by 1, and 72.84 divided by 35.5 gives me the ratio of the number of atoms, 2.05 to 2.56 to multiply by 2.05. I divide by the smallest, so I divide by 2.05. That's always the way that I solve this. So it's 1 to 2.56 divided by 2.05 to 1, 1 to 1.249 to 1. I'm looking for a number that I can multiply this by to get it up to a whole number. If I multiply it by 8, it equals 10. So 8 ones are 8, 8 1.249 is 10, 8 ones are 8, so I'll multiply through by a number and I have C8H10Cl8. That's the molecular formula. We've got alcohol A, and it's asking for a name. I always think it's best if you sort of draw it out really. First of all, either it's displayed or some kind of condensed structural formula here. So I've got CH3 twice, there you go. I've got CH, so I've got a C here with an H off it that's not seen on that skeletal section. I've got a CH here, so I've got a C with an H off it again that's not drawn on the skeletal section. You could draw the C's with the H's. Then I've got an OH hanging off this C, and I've got a CH3. So now I can see it, I can see what it is. So its longest carbon backbone is 1, 2, 3, 4. So it's some kind of butane, and if I go from this side here, it's butan-2-ol with a methyl. It's 3-methyl-butan-2-ol. Draw the structure of the organic product B formed when A is oxidized in the reaction with acidified potassium dichromate. So the OH turns to a double bond carbon to oxygen. So you get a carbonyl group, a carbon to oxygen double bond where the OH is. That's what happens with potassium dichromate. So the OH turns to the C double bond O, and that carbon that's got an H as well that's unseen on that skeletal formula loses that. So it loses an OH and the H, and it just becomes C double bond O, and then it bonds as normal to the other carbons. Two isomeric alkenes are formed when A is dehydrated. So dehydrated is removal of water. So what it does is it removes the OH from one carbon, from this carbon here, and it removes an H from the adjacent carbon. So it's going to remove the OH from this carbon, and the adjacent carbon here, this carbon here, is going to lose an H, so that's going to become CH2, and this is going to lose an OH, and there'll be a double bond between these two here. Alternatively, it could lose the OH and go the other way, because this carbon's got an H on it as well. So this carbon could lose its H, the H that's hanging off this carbon here on the skeletal formula. It could lose an H and this OH and form a double bond this way. So your reaction can form a double bond between the two carbons here in the middle, between these two carbons, and it takes the H off this C here, as well as the H off OH off this C. Remember, this C is still going to have an H here, so it's forming a double bond between the two here. Or it could form a double bond here, take the OH off here and one of the H's off there, and could form a double bond here. It's called elimination because we're removing water. So it's called an elimination reaction because we're removing H2O from the structure. Name the type of structural isomerism shown by C and D. So we've got some kind of 1, 2, 3, 4. We've got some butene, 2-methyl butuene, and I've got 3-methyl butanol here. So I'm changing the position of the carbon-to-carbon double bond. So it's some kind of structural isomerism. It's not chain isomerism because I've not shortened the chain. It's not functional group isomerism because there's still a double bond in there. That's still the functional group, but I've changed the position of the double bond. So it's structural isomerism, but more specifically it's position isomerism. List the alcohol A, product B and C in order of increase in boiling point. Alcohol A, product B and product C. So let's have a look what I've got. Alcohol A. Well, alcohol A has got an O bonded to an H, so it's got hydrogen bonding, so that's going to have the highest boiling point. Then product B has got a C to O double bond, so that's going to have a polar bond, so it's going to have dipole-dipole intermolecular bonds. That's the next highest boiling point, and these have just got no polar bonds at all, so these are just going to have van der Waals bonds. So this one with hydrogen bonding is going to have the highest boiling point, and then product B is going to have the next highest boiling point because it's got a polar bond here, so it's going to have dipole-dipole intermolecular forces, and these have got the lowest boiling point with van der Waals. Draw the structure of the isomer A that is not oxidized by acidified potassium dichromate. So you're looking for an OH on a carbon that's got 3 other carbons bonded to it. So potassium dichromate will oxidize primary or secondary alcohols, but it won't oxidize a tertiary alcohol. A secondary alcohol, like the one in the question, will turn into a ketone, and a primary alcohol will turn into an aldehyde because the OH is at the end at carbon number 1. Turn into aldehyde, and if you carry on heating it with potassium dichromate, eventually it'll turn into a carboxylic acid as well. But anyway, the question is saying which one is not oxidized, so I'm looking for a tertiary alcohol, so I'm looking for an OH bonded to a C, and therefore I can only have a methyl group, and to make the right number of carbons I can have an ethyl group here. Draw the structure of the isomer A that cannot be dehydrated to form an alkene. So you're looking for a C with an OH, and the carbon bonded to it either way has not got an H. So let's have a look at this one. So you've got CH2OH. So the OH here bonded to a C, needs an adjacent carbon to that carbon with an H, and it hasn't. So you draw out the CH2OH here, and then you put a C, and then you join other carbons off it, and there must be 3 methyl groups to make up the number of carbons. So there's no way that OH can be removed because I'm looking for an H on the adjacent C. There's no C's to the right, the only C is here, and it hasn't got an H to remove. So I'm looking for an OH and an adjacent H on 2 carbons, which would then come off on the elimination reaction and leave a carbon-to-carbon double bond in the middle, but it can't do. Name the type of protein structure in figure 3. So what have you actually got? So within the chain itself would be a primary structure, but you've got bonds between different sections of the chain. So you've got bonds here, so that's a secondary protein because you've got bonds between the actual chain itself. So if then you had bonds between one of these and another one, it will be tertiary, and then if you have them in layers and pleats, then it's quaternary. But here, so it's not just bonds within the chain, you've actually got bonds between different sections of the chain, so that's secondary. I think this bit's tough here. Explain the origin and the interaction represented by the dotted lines in figure 3 for 4 marks. We're looking for 4 things. So what have we got here? We've got a C to O bonding to an N to an H. So you need to say that the N to H is polar, so there's a slight minus, a delta minus on the N and a delta plus on the H. And similarly here, you've got a delta plus on the carbon, a delta minus on the O. I think for a second mark then you'd say that the O and the N are electronegative, that's why they get small delta minuses. That then you've got an N bonded to an H, so you've got hydrogen bonding. So if you've got an H bonding to an N, an F or an O, then you've got hydrogen bonding. And probably finally that you've got a lone pair of electrons on the O here which is attracted to the delta plus for the fourth mark. A tricky question this. N and O are electronegative, so they get a slight delta minus. It creates polar bonds. Delta plus and delta minus is between the C and the O and the N and the H. Hydrogen bond between the O and the H, because you've got an N to an H there, so that's a large difference in electronegativities. Anytime you get an H to an N, or an H to an O, or an H to an F, you get a very, very large polar bond there, a large delta plus on the H, and that's going to attract the lone pair of electrons on the O very strongly and create a hydrogen bond. Here we've got a tripeptide. It means that tripeptide, you've got three peptides. You've got three amino acids forming peptide links. Peptide link is a carbon to oxygen double bond, a carbonyl group, and an NH. So anytime we have a C to O double bond and an NH, biologists would call it a peptide link. Chemists call it an amide link. So you've got a peptide or an amide link there, and you've got a peptide or an amide link there. What's it been formed from? So before it's formed this short polymer, that C double bond O has been a C double bond OOH, a carboxylic acid group, and that NH has been an NH2, an amine group or an amino group. And similarly here, I suppose it could have been formed from a COCl, but if it's been an amino acid, and amino acids have carboxylic acid groups on the end. So it's been a carboxylic acid group, an NH group forming a peptide link or an amide link and releasing water in a condensation reaction. It can be rehydrolyzed, so the water can be added back in again, and it can break up again by adding a little bit of acid alkali in water, dilute acid or alkali. Anyway, draw a separate circle around each of the asymmetric carbon atoms. That's a carbon with 4 different groups attached in the structure. So it's not this one. That carbon's got 2 different hydrogens. That's not got 4 bonds. This is one. Here's a carbon with a group going this way, which is different from a group going this way, an H going that way, and a CH3, CHOH going that way. I think that's one there as well. Yes, it is. There's a CH, a H going one way, and no H going one way, and a methyl group, and then all this going the other way. So there's one there and one there. There's also one here as well. There's a carbon here with this CH2, four lots of CH2 and then H2, a carboxylic acid group going this way, and H going this way, and then this whole bunch of other atoms going that way. So that's one as well. So there are 3 different ones. Draw the zwitterion of glycine. Well, you can work out what glycine is because it's all of this, and this CO has been a COOH. You could also get it off your data book as well. So it looks like this. It's got an NH2 with a CH2 with a COOH here. That's glycine here. Draw the zwitterion. So zwitterion, what it does is the zwitterion has got COO minus on this end. It's lost the H, and that O has got a minus here. And at this end gets the H, and it becomes plus. So that becomes NH3 with a plus on the N. So the zwitterion looks like that. COO minus with a minus on the O, and an NHH, 3 H's and a plus on the N. You can draw it as a displayed formula or like that. Draw the structure of the species film when glycine reacts with an excess of bromoethane. Tough that. What it is it's forming a quaternary ammonium salt in 4 different additional elimination reactions. So there's a lone pair of electrons on that N, which would attack the C. So if you've got bromoethane, you've got CH3, CH2, Br. Well, that lone pair of electrons attacks the C on the CH3, CH2, the CH2 part, and the Br comes off. So in other words, a CH2, CH3 joins onto here, and every time it does so, it does it once, twice, 3 times, and it creates 3 different ethyl groups, CH2, CH3, 1, 2, 3, and the 3rd time it does it, it leaves a plus on the N because it can't then release another H. So it will form that. Deduce the name of threonine. So threonine looks like this. You could work that out from here. So you've got CH3, CHOH, CH. This bit, this C double bond OH has been a COOH here. This is your CHOH, CH3. It's drawn up here, but it's drawn down here. And this end has been an NH2 before it's bonded to the COOH on this side and formed water. So this has been an NH2. It's been an amino group or an amine group here. So this is threonine. What's its name then? Oh, tough. 1, 2, 3, 4. 4 carbons in a row. So it's bute. 1, 2, 3, 4. Butanoic acid. Butanoic acid. If this was carbon number 1, because of butanoic acid, 1, 2, 3, 4. Butanoic acid. The carboxylic acid group always is carbon number 1. So at carbon number 1, then if this is carbon number 1, you've got carbon number 2. You've got an amino group at carbon number 2. So you've got 2 amino, 1, 2, 3, 3 hydroxy. You've got to name them as an amino group and a hydroxy group because you've already used up the carboxylic acid ending. So you've got butanoic acid. So you've got 2 amino, 3 hydroxy, butanoic acid. Draw the structure of the species formed by lysine at low pH. Remember, low pH is acid. So what does something do? What do in acids? So in acid, then if we have a look here, in acid, acids produce H pluses. So where's the H plus going to go? Well, it'll go onto the ends to make NH3 plus. So at low pH, in other words, in acids, it's going to make an NH2 into an NH3. But you've got 2 NH3 pluses on lysine. This is lysine here. So this has been an NH2. And this is an NH2 here, so you draw lysine out, but instead of NH2 and NH2, the 2 NH2s become NH3 pluses. Repeating units of 2 polymers P and Q are shown. So this one's got carbon-to-carbon double bonds, sorry, carbon-to-carbon single bonds right down its backbone. So it's been formed from a carbon-to-carbon double bond. So it's been a monomer with a carbon-to-carbon double bond formed in an addition reaction. So this is an addition polymer. So it's looked like that, but instead of the 2 bonds either side, it's had a carbon-to-carbon double bond in the middle, and it's an addition polymer when the double bond is broken and form a long chain of single bonds. This one, however, looks as if it's a condensation polymer. Yeah, it's a polyester, so you've got a carbon to oxygen bond here. This is an ester bond in the middle. This is a polyester, and in between the CO and the O there, that's where the bond is formed, and that's where the bond would break again if you reacted it with something like dilute alkali, dilute base. So here, where the O is, O to C, that's been an OH. And there's an O to an H at the other end as well. So either end of this, it's had an OH and an OH there, and that OH has bonded to a CO, which has been a carboxylic acid. So this end's been a carboxylic acid, and this end's been a carboxylic acid. So the carboxylic acid end here, where the CO is and the OH is missing, has bonded to an O, which is an OH. Here it's had an OH, and it's formed water in a condensation reaction. So that's what's formed. They're the 2 monomers here, and that OH there at that end has bonded to the OH here, and this H and that OH have formed water and made the ester link, and the same at the other end, bonding to another one, and so on. An advantage of Q over polymer P. Well, Q makes water here, so when you have the alcohol reacting with the carboxylic acid, it makes water. So this reaction here is a condensation reaction that makes water. You need a little bit of acid to do that. A little bit of sulfuric acid would catalyze that reaction. But you can break it up again by using a little bit of acid or a little bit of alkali. Preferably alkali, I'd say, is a good nucleophile to use. And so the alkali, the OH minus, would break that. You could use acid as well. The advantage is that the bond's going to break if you react it with a little bit of water and dilute alkali, it's biodegradable. The justification is that that carbon to oxygen here, this carbon to oxygen bond here is polar. The C2O is polar, and so an OH minus will attack that and it'll break that bond, and an H plus will attack that and break and reform the OH and the carboxylic acid again. So CO is polar, can be attacked by nucleophiles such as OH minus, and acid will break it down as well. We've got a strand of DNA, and we've got two phosphate groups. What bonds the phosphate groups? The answer is 2-deoxyribose. That's the sugar that bonds the phosphate groups. That's just something to learn. Biologists probably already know that. Now, how do you remember which bases bond where? Well, the simple way of doing it is you look in your data book, and in your data book that you have with you in your exam, you'll have all of the bases, adenine, guanine, cytosine and thymine. Your first job is to put a lone pair of electrons on any single ends. Any single ends have lone pairs of electrons, so any ends, put your lone pairs of electrons on them, and the same for any O's. Then what you do is you recognize that an NH2, any NH2s, or any NHs, an N bonded to an H. Well, an N is very electronegative, and so that forms a delta minus, and there's a delta plus on the H. You know that because they form intermolecular hydrogen bonds. So you put a delta plus on any of the H's bonded to the N's. You do that at the start of the exam. We know this question will come up. And then what you do is you need to join the streams together, or join the bonds together. And just like I say join the streams together, that movie Ghostbusters, they say the streams will never cross, and that's going to help you, because what you do is the lone pairs of electrons on that O join to that delta plus on that NH2, so they bond to the NH2 delta plus, the electrons bond to the delta plus, and then you go round one more. The delta plus goes round the outside of that bond and bonds to the lone pairs of electrons on that N, and the O lone pairs of electrons goes round the outside and bonds to the delta plus on that H, and then the NH2, the delta plus, bonds to the lone pairs of electrons on the O, and then you end up with a fifth bond. There are 5 streams, 5 intermolecular bonds. That NH, the delta plus, bonds all the way around the outside to that lone pairs of electrons there. Let me see how that looks. So that looks like that. Lone pair of electrons bonded to the delta plus of the NH2. Lone pairs of electrons of the N bonds to the delta plus of the NH. Lone pairs of electrons on the O bonds round the outside to the delta plus of the NH2. Lone pairs of electrons on the O round the outside bonds to the delta plus of the NH2. Lone pairs of electrons on the N round the outside bonds to the delta plus of the NH. And you can see, just like in the Ghostbusters movie, the 5 streams never cross. And you can also see now that 3 intermolecular bonds form between the guanine and the cytosine, 3 hydrogen bonds, and between the thymine and the adenine, only 2 bond. So let's have a look at what the question is. Now we've got that diagram on our data sheet in our exam, this should be easy. Suggest which of the base A and B forms a pair with guanine. Well, guanine forms with cytosine. In other words, one of these is cytosine, or looks very similar to cytosine. So let's have a look which one looks similar to cytosine. We've got an NH2. That one's got an NH2. We've got an we've got an N with a lone pair of electrons. There's the N with lone pairs of electrons. And we've got an O with lone pairs of electrons. There's the O with lone pairs of electrons. It's got to be base A, but for 4 marks, we're going to say that this O with the lone pairs of electrons on top of the guanine is going to bond to the NH2 with a hydrogen bond of base A. We're going to say that the NH with the delta plus on the H of guanine is going to bond to the lone pairs of electrons on the N of base A, and then we're going to say that the delta plus of the NH2 on the guanine is going to bond to the lone pairs of electrons on the O of base A in just the same way as it did cytosine. Cisplatin works because one of the atoms on guanine can form a coordinate bond. A coordinate bond is a covalent bond. It's just that both electrons have come from one of the atoms. Instead of one atom putting one electron into the share and another atom putting another electron into the share, both of them have come from a single atom. So you're looking for an atom with two electrons, in other words a lone pair of electrons with platinum. So which one on guanine, which one, and it says another atom on guanine can form the same bond with platinum replaced another ligand. In other words, you're looking for two atoms on here, similar atoms with lone pairs of electrons, and your answer are the N's. The N's bond to the platinum. They've got a pair of electrons here and there's another N there. They're the only atoms, there's two of those. There's only those with the oxygen's got two here, but it's not two separate atoms. That's got a lone pair of electrons, that's got a lone pair of electrons. They're identical atoms. One will bond to cisplatin and the other one will bond to cisplatin as well. So your answer are those two N's. Suggest one way in which cisplatin could be administered so that the side effect of it being toxic is minimized. Administer it in small amounts. Let's have a look at this mechanism. We've got an NH2 going into an NHCOCH3. So an NH2 has got lone pairs of electrons on it. What could it possibly attack? COCH3. Well, the COCH3 has been an acyl chloride. It's had a Cl on there. So the NH2 with the lone pair has attacked a COCH3, and the COCH3 on the C there's been a Cl. It's been CH3COCl. It's been an acyl chloride. Let's have a look at the mechanism then. So what's actually happened is this benzene ring, which I've drawn as C6H5, but you could draw it as a benzene ring, no problem. NH2, lone pairs of electrons on the N, attacks the carbon of the acyl chloride. So I've got CH3COCl, and that's COCH3, so the COCH3 is going to bond to the N in a minute. So the N, with its lone pairs of electrons, bonds to the C. The first step isn't that the Cl comes off. The first step is that the double bond breaks onto the O. I sometimes say, jokingly, that O is like a loan shark. It helps out, but then it comes back and wants to reform the double bond the very next day. So it takes the double bond and it takes the electrons onto itself from the double bond, and there they are here. It forms a minus charge because electrons are moving onto the O. The N becomes plus because electrons are going away from the N. So you can see the N has now got a plus, and the O that's had electrons moved onto it has got a minus. The electrons, the pair of electrons in the bond are now on the O. And now, just like a loan shark does, it says, I'll help out, but now it wants to be repaid. So the lone pairs of electrons come back into the double bond, so that's reformed, and then that carbon's going to have too many bonds. So now the Cl breaks off, so the electrons from the bond go into the Cl, and to eliminate the N plus, one of the hydrogens breaks its bond and move the electrons onto the N plus. So what you end up with is CH3CO double bond reforming. The C has lost the Cl has gone from here, but the N is still joined on. The N is here. One of the H's is here, the other one's broken off. There's an NH, and then there's the benzene ring here. You've got an amide here. Name of the mechanism. Well, everything's added on to make one species here, and then atoms and groups are eliminated. So it's addition followed by elimination. We've got some recrystallization going on here. Why is the minimum quantity of hot water used? So the minimum quantity of hot water is used so that when you cool it back down again, so the idea is that you use hot water or a hot solvent so that the crystals that you want dissolve and the impurities don't dissolve. Then you filter off the impurities and you end up with the crystals that you do want in the water. And the reason it's hot water is that when you cool them, less crystals can dissolve and they'll come out of solution. But if you use too much water, they'll never come back out of solution despite cooling. The flask was left to cool before the crystals were filtered off, so if you cool it, then the crystals are reformed, and the colder you make it, the more crystals are formed. If you don't leave it to cool, if you leave it hot, then no crystals will form at all. So you make it cool so the crystals reform and you get a high yield of the crystals when the solution is cool. The crystals were compressed in the funnel so that the air passes through the sample and not just round it. So if you're using reduced pressure filtration or vacuum filtration, then it's sucking the air down through the filter paper and through the crystals, and you want the air to pass through the sample and not just around the outsides of the filter paper. A little cold water was poured through the crystals just to wash away any impurities. There'll be soluble impurities. They've got to be soluble to dissolve in the cold water that's washing them away. The melting point of the sample was found to be slightly lower than that in data book value. State the most likely impurity. Well, always the most likely impurity is water, and the way that you get rid of it is press the sample of crystals between filter papers. That's always going to be the easiest way to get rid of the main impurity, which is water. So what have we got here? We've got 5.05 grams of phenylalanine. Well, we know what phenylalanine is. It's like this. There's 1, 2, 3, 4, 5, 6 carbons in a ring. Every carbon here has got a hydrogen on it. So there's 1, 2, 3, 4, 5 hydrogens, an N and 2 H's. So you've got 6 times 12 for the carbons, 1, 2, 3, 4, 4 times 1 for the hydrogens, and you've got 14 for the nitrogen and 2 more for the 2 hydrogens. So you can work out the MR. The MR of phenylalanine comes out as 93. So I've got the mass of phenylalanine 5.05. So moles is mass divided by MR. I've got 0.054. I know that from here 1 mole of this makes 1 mole of this. So 0.054 moles of phenylalanine should make 0.054 moles of the product, theoretically, if there's no waste. Now, the MR of the product, the purified product, in step 1, I can work out the MR of this. So 6 carbons, 12 each, 5 hydrogens, 1 each, 14, a 1, a carbon is a 12, and oxygen is a 16, carbon is a 12, and 3 H's are 3 1s. And it comes out to be 135. Now it tells me that the amount of product that's made is 4.82 grams. Well, if I convert the mass, if I know the number of moles of product that I make, which is 0.054, which is the same as the phenylalanine, I can, moles is mass divided by MR. I've got 135 as my MR. I can work out the mass, which is 0.054 multiplied by 135. 7.33 grams should have been made. I've only made 4.82. So my yield is how much I did make, 4.82, the smaller figure usually, divided by 7.33 multiplied by 100%, 65.8%. Write an equation for the reaction of this intermediate in step 2. So let's have a look at step 2. So in step 2, I've got an NO2 joining onto the ring. So here, in step 2, I've got an NO2 joining on the ring. This part isn't changed. To get an NO2 joining onto the ring has got electrons in it. It attacks positive species, so it makes NO2+. I get that, by the way, NO2+, from reacting concentrated sulfuric acid, H2SO4, with concentrated nitric acid, HNO3, and it makes NO2+, and water, H2O, and HSO4- ions. But I've got an NO2+ now, and it will join onto the ring, and it will release an H from the ring, and that will be plus. So the plus is transferred onto the H as the H has been replaced. Name and mechanism. Well, this is an electrophile. It's an electron pair acceptor. It's going to accept an electron pair from the ring when the ring attacks this. So it's an electrophile, and it's replaced the H on the ring. So the NO2 has replaced the H. It's electrophilic substitution. Suggest the type of reaction occurring in step 3. Let's have a look at step 3. So step 3, what's step 3 done? Right, it's broken that bond there. NH2 has been formed from NH2COCH3. That's an amide bond, or a peptide bond that's been formed there, an NHCO. That peptide bond, or that amide bond, has been broken. Well, when you make an amide bond between an amine, an NH2, and a COOH, a carboxylic acid there, it releases water. You can put the water back in by reacting water with it and with a little bit of dilute alkali or base, OH-, acts as a catalyst. I can replace the water back into that bond. So when I've made that bond, I've released water, condensation reaction, and when I put the water back in, it's called hydrolysis. Hydrolysis means using water to break bonds. Identify the reagents used in stage 4. Let's have a look at stage 4. Stage 4, I've turned an NO2 into an NH2. Well, there's two ways of doing that. To replace the O's with H's, I can either use hydrogen and nickel catalyst, or I could use tin and concentrated hydrochloric acid. Hydrogen nickel is probably the easiest one to remember. So I've got an organic compound. Let's have a look what I've got. I've got an alcohol group there, so I can tell at around about 3,500 here. I've got a broad absorption peak here, so I've got an alcohol group here. It's hydrogen NMR. It's got a splitting pattern. It's got 4 different hydrogen environments. 1, 2, 3, 4. The integration patterns 0.4 to 1.6 to 1.2 to 2.4. So if I were to divide by the smallest, that's 1 to 4 to 3 to 6. Okay, let's have a look then. Table A on the data sheet shows that I've got a 3360. I've got an OH alcohol present. Okay, what else do I know? Well, I've got 4 different peaks showing 4 different hydrogen environments. I've said that before. There are 4 different peaks here, 1, 2, 3, 4. And if I take the integration numbers and divide by the lowest, I'll find the ratio of each. So my ratio is 4 to 1 to 3 to 6. Now then, what have I got? I have got 1, 2, 3, 4, 5, 6 carbons in there. Yes, it's C6H14O. So I've got an integration pattern of 4, 1, 3 and 6. So what have I got? 4, 1, 3 and 6. Well, one of the H's is going to be an OH, so I know my 1 is an OH. So I know that for a start. So I know that one that's got an integration pattern of 1 must be the H on the OH. I know I've got an OH here. Now I've got 4, 3 and 6. Usually a 3 is a CH3. So 3 hydrogens on a CH3. So this is my 1 H. Then I'm looking for a 1.2. This is going to be 3 hydrogens all the same. It's probably going to be a methyl group. Okay. What have I got then? So I've got a methyl group where there's a 3. A 6 is usually 2 CH3s in a different environment, but 2 CH3s bonded to the same carbon usually give you 6. So we're looking at a triplet, 2 CH3s there. And then finally I've got a 4. What could a 4 be? Well, I can't have CH3 is 3 hydrogens. I can only have a 4 by having 2 identical CH2s. That's all I can have. And so I've got CH3 is the 2 CH3s are on each end. I've got a CH2 and a CH2 on each end, so that's going to give me my symmetrical pattern. 2 CH3s on either end, a CH2 then next in, and they're identical, and then all I want is something symmetrical in the middle. A COH and a CH3 will fit the bill. Write an overall equation for the reduction of butanol. So reduction is adding hydrogen to represent, using H with the square brackets to represent the hydrogen that's being used as the reductant. So hydrogen's been added, and the way that we're going to show that is with the square bracket around the H. First of all, we need butanol, which is CH3, CH2, COCH3, and we're going to need 2 H's because that's CO. That ketone, that butanone, is going to be reduced into a COH and an H. So the C double bond O becomes a COH, and the carbon needs another H off it. Therefore, it becomes a secondary alcohol. So it becomes butan-2-ol. By considering the mechanism of the reaction, so how does it actually happen? So you can use a hydride ion, a H- ion, that's going to be a nucleophile and attack that C. That's the way it's going to go. It's going to attack the C, and then the pair of electrons on the double bond oxygen will go onto the O, and then an H plus, because it's probably in methanol. The H plus from the methanol will then bond on, so there'll be a lone pair of electrons on the O, which will have a minus bond onto the H plus. So how does that happen then to give a product that's got a plane polarized light? So first of all, the H minus is a nucleophile, so it's going to be a nucleophile and it's going to attack the C. This is planar, this is flat, so the CO is a flat. It's only going to have 3 bonds, a double bond to the O and a bond either side to either carbon, so it's only got 3 atoms bonded to it, so that's flat. It's not got 4, it's not tetrahedral, so it's going to be flat. So the H, or the H minus, the hydride ion, can attack from the bottom or from the top. It can attack from above or below. That's going to create 2 different enantiomers, 2 different mirror images of each other in equal amounts, because there's an equal chance of attack from top or from bottom or from above or below. There's an equal chance of this hydride ion, this nucleophile, attacking from above or below. So that equal chance creates equal amounts of each of the 2 enantiomers, and that's called a racemic mixture, where you get 50% of each enantiomer. Therefore, there's going to be no overall optical activity, because each of the 2 enantiomers rotate plane polarized light equally, but in opposite directions. So therefore you're going to get no rotation of plane polarized light with a racemic mixture. Butanol reacts with a reagent in the form of HY. There's no such thing as Y. To form a saturated compound, so with single bonds. Suggest a reagent in the form of HY that could react with butanol. So the double bond of butanol will react with something like hydrogen bromide, HBr. Draw a mechanism. Well, it's going to be electrophilic and it's going to be addition, because this will add across the double bond. And what will actually happen is the mechanism will look like that. The double bond will actually attack the H. That's not a very good drawing. That double bond, the electrons will bond to the H and the Br will break off. Now where's the H go? It goes to the left-hand carbon, the carbon that's got the most hydrogens on. So that carbon's got 2 hydrogens, that carbon's only got 1. So it joins the carbon already with 2 hydrogens with the most number of hydrogens. So there it is, it's joined that to make a CH3 instead of a CH2. Now this carbon hasn't got enough bonds, so that forms a carbonium ion, a C+ ion. It's a secondary carbonium ion because it's got 2 other carbons bonded to the C+. Secondary carbonium ion is more stable than a primary carbonium ion, and we'll talk about that in a minute. So the Br has had minuses, it's got a minus, it's got a lone pair of electrons, the pair of electrons from the bond has gone on to the Br, and then that will attack the secondary carbonium ion here and form this compound here, which is going to be butane. It's going to be 2-bromobutane. Explain how 3 isomeric products are formed when HY reacts with but1ene. Well, this is the major product where the H bonds to the C with most H's and forms the more stable secondary carbonium ion. However, the H could bond to this one and form a plus here, so the plus could be on this carbon instead, and this could have 2 H's, so the H could bond to this one and leave this one as CH2 with a plus, and the Br could join onto that, and it would create 1-bromobutane, so it could end up as a position isomer of this. But it's less likely to do so. It's a minor product, so it will do it to some extent, but not very much, not as much, because that primary carbonium ion will be less stable than the secondary carbonium ion. Where's the third product going to come from? Well, we've made a chiral carbon here, so these are going to have enantiomers, so this is going to be optically active because that carbon has got 4 different groups attached. So that's your answer. The major product here exists as a pair of enantiomers, and the third one is 1-bromobutane because it's obtained by as a minor product when a primary carbocation is formed instead of the secondary carbocation, which is more stable.